write down an effective theory for the Goldstone bosons. Okay, so what we said is that we have a global symmetry that necessarily gives you a valley at the bottom of the potential, yes, just by the fact that there was a global symmetry spontaneously broken, there has to be a valley, and this valley is nothing else but taking the symmetry generators and acting, on one of the vacua. Yes? If the symmetry generator is unbroken, you will stay at the same point. That's what it means that the symmetry is unbroken. If that particular direction is broken, you will have to move. That's what it means that, the symmetry is broken. Yes? But it's a symmetry, so it must connect points with, equal potential. So you must remain at the bottom of the potential. So the motion along the bottom of the valley must be described by simply taking, one of the points of, one of the waves, yes, and just act with the broken directions on the wave. Yes? So that's how you are going to describe these Goldstone fields. So that's where we ended up. Yes? So this is how we are introducing an effective theory for the Goldstones. Yes? So we have our wave U0 and simply act in the directions that are broken. Sometimes they are denoted by a hat. I will not bother writing those hats, but so these are just the broken directions. Yes, and these epsilons, these transformation parameters, are now going to be promoted to be literally the fields, that are parameterizing the motion along the valley. So those will be promoted to the pion fields. Okay, so this is how, out of just an ordinary global transformation, we are going to get the Goldstone field. And of course, this is usually dimension 1. So there will be a parameter which is usually called the pion decay constant showing up. Okay, so this is what is called the nonlinear field. Or the sigma model field, many different names for it. And again, what this is supposed to give you is an effective theory, a low energy effective theory that is describing purely the Goldstone excitations of the theory. So this is an effective theory for the Goldstones. And it's an effective theory in the sense that, of course, the theory with the global symmetry breaking has more fields in it than the Goldstone itself. Yes, but the Goldstones are the ones that are light. They are the ones that are describing the excitations around the bottom of the potential. Yes, so for example, if you have, if you just started out with the theory of scalar fields, of course there will be some radial direction. They will be massive. Yes, and those are not part of this effective theory. Yes? So this effective theory necessarily has some built-in cutoff scale. Yes, where some of these new particles are going to come in. Okay, so this is an effective theory with a cutoff. Yes. And the cutoff is going to signify the place where some of these particles will have to show up. Okay, so some of the new particles have to show up there. Oops. So as I said, one example is, just literally take the Higgs doublet of the standard model. Yes, it's a theory with scalars. It has, 4 degrees of freedom. And as you know, there are 3 Goldstone bosons, and you can write literally a nonlinear field that is parameterizing the 3 Goldstone bosons of the Higgs. And the Higgs particle itself is going to be the one that is not part of this effective theory, yes, because that's a radial mode, yes, that is a massive mode that is integrated out. Yes, that's one example. The other one that we'll be discussing in a moment is when you don't have an underlying scalar theory that is giving rise to the global symmetry breaking, like for the case of QCD, and then there will be a bunch of other particles also, a bunch of non-Goldstone modes, and they are just going to be the other bound states, the massive bound states that are formed, you know, in the strong interactions. So let's try to talk about that example, because that's very useful one to understand. So let's talk about QCD and its chiral Lagrangian. So this is an example that hopefully is somewhat familiar to everybody. And of course I will not, you know, talk about the origin of QCD. So there you have the QCD Lagrangian. It's an SU3 gauge theory. And for now, we are just going to take it with 3 flavors. So we are just going to take up, down, and strange, the light flavors. So you have your gluon Lagrangian, G mu nu A, G mu nu A. Yes. And then you have your quark Lagrangian, yes, Qi bar, ID slash minus M Qi. Yes, and then I here is the flavor index. So here are the quark masses. So this is a quark mass matrix. Yes. Now the important part of this QCD Lagrangian, at least from the point of view of the symmetries and global symmetry breaking pattern, is that in the limit, when this quark mass is very small, this QCD Lagrangian actually has a very large global symmetry. So in the limit, when MQ goes to 0, QCD Lagrangian has an SU3 left cross SU3 right global symmetry. In fact, it's actually a little bigger than that. It's actually U3 left cross U3 right. So there are 2 additional U1s. One of them turns out to be baryon number, is a real symmetry. The other one, the axial one, turns out to be anomalous. We are not going to discuss it for now. It doesn't, you know, doesn't play a role, at least in the story that we are discussing here. Of course, you know, it has many nice consequences, but we are not going to talk about that. So the origin of this SU3 left cross SU3 right global symmetry is the same story as I was mentioning yesterday when I was trying to tell you about, you know, why fermion masses don't have a hierarchy problem. Yes, it's just, you know, if you take a general 4-component Dirac fermion, you can write it as two-component Weil spinors. Yes, so this would be also, Lance was mentioning this yesterday, yes, today. Yes, you have a left-handed and the right-handed 2-component fermion. Yes, so from the point of view, if you think of this as a Dirac fermion, yes, let's say for QCD, these would be in the fundamental of the color group. Yes, so both chi and psi bar would be a, you know, in a 3, a fundamental of the color group. Of course, you can write it instead, you can write it in terms of two-component left-handed fermions. Yes, so if I write it in terms of chi and psi, yes, now these are both left-handed fermions, yes, because I took a conjugate here, but then chi is in the fundamental and psi would be in the anti-fundamental of the color group. Okay, so you can write it as 2 left-handed fermions, and then one is a fundamental and the other is in the anti-fundamental. Yes, of course, you know, it's completely equivalent. And the important thing, as I mentioned yesterday, was that, of course, you know, the kinetic term for these 2-component fermions, they don't mix among each other. Yeah? So the kinetic term you can write as I times chi dagger sigma bar mu d mu chi. Yes. And the same thing for psi. Yes. So usual, kinetic term, and it's only the mass term plus chi goes to psi, and then there is the mass term that is going to mix the left-handed and the right-handed components with each other. Yes? So in the limit, when the mass goes to 0, yes, I will have the 3 left-handed fundamentals of QCD. Yes, so the up, down, and strange left, and you can actually mix them among each other with an SU3 left symmetry, and then you can have the 3 left-handed anti-fundamentals, let's say the psi fields, as you can mix those among each other. Yes, and those are 2 separate SU3 symmetries. Yes, so the flavor symmetry of QCD in the limit when the quark mass goes to 0 is actually SU3 left cross SU3 right. Yes, so that's really important. And I assume everybody knows that. So you have psi goes to u right, psi, and chi goes to u left, chi. So these are 2 separate 3x3 unitary matrices that in flavor space, yes, and you can do these rotations and leaves the Lagrangian invariant. Okay, very good. So that's nice. So we have this SU3 left cross SU3 right global symmetry of QCD. Yes. And the naive expectation is that when you look, so QCD of course is a strongly coupled theory, it will form some bound states. Yes, and the naive expectation is that, well, you have this global symmetry. The global symmetry should be realized also on the bound states. Yeah, so the naive expectation would be that it should be realized on the bound states. Again, for now I just introduced 3 flavors of quarks, so up, down, and strange. Yes, so that's why, so this SU3 is a rotation in this flavor space. In this, of course, in addition, everything has a color index, and that's of course understood. Yes, all of these are fundamentals of color. Plus, we have the 3 flavors. And in the limit, when the quark masses go to 0, you can rotate the 3 flavors among each other, and that's going to give you the additional symmetry. Okay? That you can just separately rotate the left-handed quarks and separately, independently rotate the right-handed quarks, and that's still going to be a symmetry of massless QCD. Okay? So the expectation is that this should be realized on the bound state spectrum. Of course, as all of you know, what actually happens is that the bound state spectrum of QCD does have a very large, nice global symmetry, yes, which is, the whole thing, the whole story of the early 60s. Gell-Mann was able to, characterize the bound states by putting them into multiplets, but he put them in multiplets of a single SU3. Yes. So there is some global symmetry. Of the bound states, but it's only a single SU3. So there's no doubling. So SU3 of Gell-Mann. Yes. So you can classify the bound states of QCD according to multiplets of a global symmetry, just like you're expecting it, but it turns out that it's actually not as large as it naively appears from the Lagrangian, yes, but it's smaller. Okay. So the question is, what happened to the remaining global symmetry. Yes? And there is one plausible way out without a contradiction, which is, well, you know, the QCD dynamics is complicated. Yes? And in particular, the vacuum of QCD can be different than, you know, the naive vacuum of the perturbative theory. Okay, so the way out is that the QCD vacuum is non-trivial in the sense that actually in the QCD vacuum there is a condensate for some of these quark fields. Okay, and of course you want to make sure, you know, that the vacuum that you are actually observing is such that it maintains one of the SU3 symmetries, because that's the one that is observed. Yes, that's the one from the eightfold wave for which Gell-Mann got his Nobel Prize. Yes, and the other one, another combination of the SU3s, should be spontaneously broken. Okay, so the way you can achieve that is by assuming that there is actually a quark condensate. Yes, well, it should be a bilinear. Yes, because we know that Lorentz invariance is not broken, so these quarks are fermions, so it should be a condensate of bilinears. Yes, and it should have the kind of quantum number that leaves one combination of the SU3s invariant. Yes, and the other combination of the SU3s is going to be spontaneously broken. Yes, so if you think of this in terms of flavor space, yes, so first of all, again, you know, we know that, you know, color itself is not spontaneously broken. Yes, so these will be, you know, the color indices are contracted here. Yes, and what you will get here is a structure in flavor space. Yes, and that one should be proportional to the unit matrix in flavor space. Yes, and there will be some parameter here. Let me just make it proportional. You know, proportional to the appropriate scale of QCD itself. Okay, so again, just to understand exactly, if I write out these 4-component fermions instead of the 2-component, in terms of the 2-component fermions, yes, the way this will look like is that it's Q bar left I, Q right J, plus Hermitian conjugate. Yes. So if you look at the structure, what you see is that one combination of the SU3s, namely the one where you rotate the left and the right-handed quarks with the same matrix, yes, so that one is going to be remaining invariant if this is truly the unit matrix showing up here, yes, because you will have one of them rotates with the matrix, the other one rotates with the same matrix, but there is a dagger here, yes, so you will have a U dagger times U. Yes, and that, if it acts on the unit matrix, is actually going to leave the vacuum invariant. Yes, so if you take U left equals U right, yes, so that's what is called the vector-like subgroup of SU3. So this is called SU3 vector. Okay, so this would indeed leave this QCD vacuum invariant. So this is unbroken. So this is Gell-Mann's SU3. But the other combination, yes, where left is not equal to right, but one of them is equal to the dagger of the other, yes. So U left equals U right dagger. Yes, so that's what is called the axial combination. SU3 axial. Yes, so this is the one that is spontaneously broken in the QCD vacuum. Okay, so that's, you know, that's a very nice picture, but of course it has an immediate consequence. If there is a spontaneously broken symmetry, yes, then there's gotta be corresponding Goldstone bosons. This is a broken SU3, so you expect there to be an octet of broken Goldstone bosons corresponding to these broken directions. Yes.
But you said that we had U3 times U3.
Right.
So it's baryon number and axial
Right.
number.
So baryon number is an observed symmetry, so that, I didn't add that. That's, of course, also part of the classification of the spectrum. And it turns out that the axial U1, so that's actually not spontaneously, so that would also be broken by this VEV. So then the question is there a ninth Goldstone boson? Yes, and the answer is not really, because there's an anomaly. Okay, so again, that's a whole set of separate lectures, so this is called, how instantons are actually, solved. So this used to be called the U1 problem. So this in the 70s was sort of a true puzzle, why there is no ninth Goldstone boson called the eta prime. Yes, because, people, of course, there is a particle that is the eta prime, but its mass is quite a bit heavier than what you expect from it being a Goldstone boson. And, there were actually specific relations. Weinberg, had a particular formula that was violated by it. And, so the answer is that actually, the effect of anomalies, and in particular instantons, is going to push the mass of this eta prime to be heavier. Okay, so I'm not going to focus on that. If you're interested, there is a big literature. We can also talk about it. But the story is just that, yeah, you may naively think there are 9, but there are only 8, and there's a subtlety there related. And that subtlety, again, was a big topic. Yes, it's called the U1 problem, and it's actually non-trivial. Even when you think about instantons, how it exactly it is resolved is a complicated story, but there is a clean picture there. Okay, very good. Any other question? So 8 Goldstone bosons. Yes, so those are the ones that are the pions, and then the kaon, k plus minus, k0, k0 bar, and eta. Okay, and again, so these are so-called pseudo Goldstone bosons, of course, in the sense that there are these particles in QCD which are very light, much lighter than all the other bound states that you are observing, but of course they are not exactly massless, and we are not shocked by that either, yes, because of course the symmetry that was spontaneously broken also was not an exact symmetry, yes, because this SU3 axial was a good symmetry only in the limit when the quark masses went to 0. Okay, so these are so-called pseudo Goldstone bosons. Meaning that they are not exactly massless, and we will discuss in a moment how to estimate the effect of the breaking term on the mass of these Goldstone bosons. Okay, very good. So the first question is, where is the Electroweak symmetry? Actually, it turns out that it's relatively nice story, yes. What you have is that you have the SU3 left cross SU3 right symmetry of QCD, and that actually includes the Electroweak interactions, yes, because you know that the in the standard model, the up and the down quarks, yes, the left-handed ones form an SU2 doublet, the right-handed ones are SU2 singlets, yes, so the expectation is that the SU2 Electroweak of the standard model is actually embedded inside this SU3 left. Okay, so the expectation is that the SU2 left of the standard model is actually embedded into the SU3 left of the flavor symmetries of QCD. Yes. The story is a little more complicated, and again, it's something that I will not go into detail. Yes, really, what you have is these guys are SU2 doublets. Yes, but really, charm and strange left are also SU2 doublets. Yes, so the true way to really embed this, the SU2 of the standard model, would be to take a 4-quark QCD. Yes, embed SU2 twice. Yes, both here and here, but then it turns out the charm is very heavy, yes, at least compared to the scale of QCD, and integrate out part of that, and then look at the resulting effective theory. Okay, people usually don't do it, we are lazy, so we will just pretend that SU2 left is just, connecting up and down, but the true, more complicated structure would be embed it twice, get the effective theory, and then make the charm pretty heavy, and get rid of, the part of that multiplet. But again, it will be lazy, and we'll just, do the naive thing and just identify the upper 2 component with SU2 left. Okay, very good. And actually, hypercharge, yes, can also be embedded. So hypercharge is just, you can check the quantum numbers, is just the third component of the right-handed SU3. Yes, plus baryon number over 2. Of course, it depends what normalization you use, but okay, very good. So standard model is basically embedded into the global symmetries of QCD. Okay, very good. So now let's try to truly write down an effective theory for the Goldstone bosons. Yes. So write an effective theory for the Goldstones, for the pions, these pions here. Yes? I'm sorry? This is electroweak hypercharge, yes. Right. So now I would like to get the effective theory for the pions. And in particular, I will be really interested in how to write a Lagrangian, how to get the interactions among the pions. Yes? And the other thing I would like to see is how to introduce the effects of the explicit breaking terms that are making the Goldstone a pseudo-Goldstone boson and giving mass to them. Okay? So well, I told you how to write a field that is representing the pions, the Goldstone bosons of a generic theory. What we are supposed to do is we are supposed to take the VAV, yes, that is giving rise to the breaking, yes, and then just act with the generators along the broken directions on that VAV. Okay, so we know the structure of the VAV, yes, it's Q bar Q. Yes, so this is what is breaking the global symmetries in QCD. Yes. So now the question is, how does this field, that this combination of the fields that is getting an expectation value, transform under the global symmetries? Yes. Well, one of them, I wrote it out here. Yes. One of them is a left-handed guy, and the other one is a right-handed guy. Yes. So this combination of the fields that is eventually getting an expectation value can be identified as a bifundamental of the SU3 left cross SU3 right global symmetry. Okay, so this is a bifundamental of SU3 left cross SU3 right. Okay, so I can think of this U0, yes, so the VAV that I'm using in order to build up my nonlinear realized Goldstone fields, yes, as the VAV of a 3x3 matrix, yes, so that 3x3 matrix is representing, this combination of the fields that are, a bifundamental, yes, so this is representing, an object that would have transformed from the left with the left-handed field and from the right with the dagger of the right-handed transformation, and then if you want, you can put a scale here, you know, so this is a convention-dependent thing. Sometimes people put a scale here, sometimes people, you know, write just the direction without the VAV, and, you know, you have to go back and forth between them. Okay, so this is the VAV, yes, and to get the Goldstone field, yes, what you're supposed to do is you're supposed to just act with this, act on this direction that is, you know, that is giving you the vacuum direction, yes, with the broken generators. Yes, so first of all, how would a bifundamental in general transform? Yes, so in general, you would say that you have a U left times this U0 times U right dagger. Yes, so this would be the general transformation of a bifundamental. Yes, but of course, some of these directions are unbroken. Yes, so the direction where left equals right, yes, because U0 is proportional to the unit matrix, that direction is the unbroken SU3, again, Gell-Mann's SU3, the SU3 vector. So what you are supposed to do is, in order to get the broken directions, is to identify the directions corresponding to the axial SU3, yes, so that direction is when U left equals U right dagger. Yes, so the U left equals U right. Yeah, so this is the unbroken direction. Yes, and then the U left equals U right dagger. That's the broken direction. Yes, and that's the one that I'm going to identify with the direction for the pions. So I'm going to write U left as e to the I pi ATA over F. Yes, and then that's also U right dagger. So how will this field look like? Yes, well, is this times the unit matrix times this thing again. Yes, so I can just write it as e to the 2 pi ATA over F. And again, you know, I can put an F here or not. That's a matter of convention. So this is now how to write. So this is the nonlinearly realized Goldstone field for the specific case of QCD. Yes, so this is the pion field for QCD. We can go ahead and ask the question, how does this field transform under the various symmetries? Yes, by the various, I mean the broken and the unbroken symmetries. Well, we know how they transform, yes, because we know that Ux in general goes as U, Ux, U right dagger. So under the unbroken symmetries, yes, so the unbroken symmetries, U left equals U right dagger, and I'm just going to call it U vector. So Ux just goes as U vector, Ux, U vector dagger. Yes, so really under the unbroken symmetries, it transforms as an ordinary normal linear transformation in the adjoint of the SU3. Yeah, again, you know, this is a matter of convention, yes, what exactly you put there. And I'm sorry? You not. It points in that direction, but again, you know, what exactly stands there doesn't quite matter, because what you want eventually is to have a canonically normalized kinetic term for it. So you will eventually rescale by an overall factor the whole thing anyways. Okay, what matters is that you pick the right direction, yes, and what exactly you are going to put there, you know, it doesn't quite matter, because, you know, as you will see, so most people don't even put anything here, yes, and just write a dimensionless field and then, you know, try to make up every dimension with the VAVs. Okay. All right. Very good. So again, how do these Goldstone fields transform? Well, under the unbroken symmetries, yes, it transforms like an ordinary adjoint linearly under the SU3 diagonal. So this is a normal linear transformation of an adjoint. Yes. Again, if you want to write it explicit, to be explicit in terms of the pion fields, you can take this. Yes, you can write it as e to the 2I pi t over f. Yes, sometimes I will just write it as pi over f. And if I don't write indices, then it's understood that this pi is actually a matrix, which is pi a times ta. So it's a 3 by 3 matrix where you're arranging them with the SU3 Gell-Mann generators. Yes, and so you can just go ahead and this would be the transformed pion. Yes, this would be the untransformed pion, pi over f. You can expand these exponential, and you'll just see that pi goes to uv, so pi uv dagger. So just normal, ordinary linear transformations under the unbroken directions. Yes. Now, of course, under the broken directions, it's going to be more complicated. And that's where you see the nonlinear realization of the symmetry. Yes, under the broken generators, yes, I have to do exactly the same thing, except now UV and UV dagger are not the same thing. Yes, so the way I'm supposed to write this whole story is that e to the 2I pi prime over f is equal to UA e to the 2I pi over f UA. Yes, and now this this is an SU3 direction, so I'm going to still parameterize it as just a transformation e to the 2I c ATA over f. So this is supposed to be a global transformation, yes, where I made the left and the right transformations to be equal to each other. So these CAs are just the parameters of the broken part of the global transformation. So these are some constant numbers here, yes, just saying how much, what kind of broken transformation I have tried to do, yes, and okay, so you can write it like this, 2I pi over f e to the 2I CA TA over f. Yes, sorry, there's no, let's say that these are dimensionless transformation parameters, yes, so these are normal epsilons, yes, just transformation parameters in a particular direction. And then you can start, comparing the left and the right hand side order by order. Yes, so I can expand this left hand side here, the exponential 1 plus 2I pi prime over f, and that is 1 plus 2I CA TA times 1 plus 2I pi over f, 1 plus 2 CA TA, yes. And of course the important thing is that because this is an axial symmetry, there's no minus sign here. So the leading terms here, yes, when I just take 1 times C, yes, those terms now do not cancel out. Yes, so actually there's going to be a linear constant shift, yes, in this transformation direction. Yes, so what you will find is that the very leading effect of this axial transformation will be to actually shift the pion field. Okay, so the leading term doesn't cancel. Linear in C doesn't cancel. Yes. And that will tell you that pi a prime TA will go over is the original pi a TA plus f CA TA. Yes, plus order, higher order terms in the in all the other fields. So to leading order, yes, there's got to be a shift in the pion. Okay, so this is the famous shift symmetry. Yes, it's of course it's not exactly a shift symmetry. There are higher order terms here. Yes, but to lowest order there's a shift symmetry. Yes, and that's very different than the usual transformation rules of linearly realized symmetries. Okay, so this is the famous shift symmetry. And again, this is again what is telling you that there can be no non-derivative interactions for a pion showing up, at least as long as the pion is an exact Goldstone boson, yes, because that would break the shift symmetry. It also tells you that, you know, the pion must be massless, yes, well, it cannot have any non-derivative interactions, so etc. So that's a very nice and simple result, yes. Then the next question is, so we roughly understand the field and the transformation properties of these Goldstones. Now I would like to literally write down a Lagrangian for these Goldstone bosons. So how to write a Lagrangian? Well, you know, I have my field. I know what kind of symmetries it has to obey. It has to obey both the broken and the unbroken symmetries. So I'm just going to try to write down terms in the Lagrangian that are invariant under both, you know, under the full original SU3 left cross SU3 right symmetry. Okay, so just write all terms that are invariant. Okay, how should I do that? Well, what is the simplest thing? There is a simple invariant term. Yes, there is a term that is invariant, which is the trace of U dagger U. Yes, so that's a very nice and simple term because it doesn't depend on the Goldstone boson. So this is just a constant. So there's, again, as you expected from our discussion, there is no term that has no derivatives in it. Yes, and that's again a consequence of this shift symmetry that we have discussed previously. So it's a term with no derivatives. Yes, is a constant. It doesn't contain the Goldstone bosons. Yes, because U dagger U, you need to take the trace of U dagger U to make it invariant under the SU3 left cross SU3 right symmetry. But once you made it sufficiently invariant, the dependence on the Goldstone boson completely dropped out. Yes, because again, you know, this is e to the I pi, this is minus e to the minus I pi. Okay, so then there will be terms that are higher order in derivatives. So there will be the next term, and that's the most important one, the term with two derivatives. Yes, so you can take a derivative d mu of u, yes, and then ask the question, how does this transform under the global symmetries? Yes, so it's still a global symmetry. So here, of course, you write it as e to the I pi a of x t a over f. Here this is a field, yes, but under the global symmetry, the transformation parameters are still space-time independent. Yes, so that's still important to remember. Under the global symmetry, of course, it still transforms with the u left, so it transforms exactly the same way as the term without the derivatives. Yes, so to make an invariant out of it, yes, you do exactly the same thing. Yes, you just take this term and then you dagger it. Yes, and then you take the trace of that. Okay, of course, the big difference is that now, because I have a derivative, yes, the Goldstone field no longer drops out. Okay, but again, this is in nice agreement with our expectations that at the derivative level, of course, there can be and there will be non-trivial interaction terms for the Goldstone bosons. And this is the term that is going to capture the one with the lowest number of derivatives, meaning as you go to very low energies, this is the one that is going to be the most important term. Yeah? So this is the kind of structure that people have been using to, you know, just build up the interaction Lagrangian for the pions from the bottom up. Yes, just take the terms with the smallest number of derivatives. There's only one. Then, of course, you can start looking for invariants with more derivatives. As you go to slightly higher energies, those will be more, you know, start to become important also. At the lowest level, this is the only term that matters at the lowest energy level. Okay, so this is the leading term in the limit when the momentum over F goes to 0. Yes? So in the limit when the characteristic interaction momenta of these pions are much smaller than the scale F, and of course we will have to ask the question, what is F? And I'll tell you that in a moment also. Okay, so you can just go ahead and, you know, write this term. Yes, you can expand it in terms of the pion fields, and what you're going to find is that, of course, there will be a kinetic term for the pions. Yes, whatever that kinetic term is, that will fix the overall coefficient of this invariant. Yes, because you want that kinetic term to be canonically normalized. Okay, so if I think of F, if I think of U, something that is multiplied by F, then it turns out you have to put an additional factor of F squared over 4 in order to get the correct normalization for this for the kinetic terms that you're getting from there. And if you put that, then everything else is fixed. Yes. So in particular, you will find then the kinetic terms d mu pi a squared. Again, it's canonically normalized because I insisted on it, so that's not a miracle. I just put the coefficient in front such that it comes out right. Yes. But the important thing is that then there will be an additional term that will look like 1 over F squared times d mu pi times pi squared. Yes. And then there's an overall constant here which I was too lazy to actually calculate. Yes. So, and higher order terms. Yes. So for example, this term is the one that is going to specify the lowest order 4-point interactions among the pions. So the pi go to pi scattering, yes, is going to basically be fixed by that particular term. Okay, very good. So, and of course, as I said, you can expand this to higher order, or you can start writing terms with more derivatives, and that has been a real, you know, research area in the 70s and 80s. It was called, you know, doing chiral perturbation theory, and people were, you know, writing more and more terms, and then trying to fix, you know, of course, once you write more terms, then there will be more coefficients, so some of them you have to fix from experiments, and, you know, this is an important direction, and as I said, you know, this has been carried through to pretty high orders. But of course, that's not the main direction we are trying to go. We are trying to eventually use this for composite Higgs models. So the next question is, once we understand how to write the terms specifically just, yes? Let's see. Tell me when it's better. Does it sound better now, or? Okay. Just let me know if it's again doing weird things. Okay, so the next question is, now I understood how to write, you know, the Lagrangian purely for the Goldstone bosons, and then the next question is, how am I going to write the interactions of these Goldstone bosons with the Electroweak group? Yes. So the interaction with W and the Z, or photons. Okay, well, that's pretty clear. Yes, that's why I already told you where I'm going to embed the Electroweak interactions into the global symmetries of QCD. So to include interactions with the W and the Z, Yes, well, all I do is I just identify how the SU2 left cross U1 hypercharge is embedded into the SU3 left cross SU3 right cross U1 baryon number. Yes. And then just promote the ordinary derivative to covariant derivative. Yes. We know how to do that. We know how to gauge a global symmetry. Yes, that's how when you're learning gauge theories first, you always start out with a global symmetry. Yes, and then you know how to gauge that. So we have that specific procedure here also. And so you can, as I said, you know, I'm going to be lazy and we'll just do the naive thing that, for example, the SU2 is embedded as a 1/2 tau A into SU3 left. Yes. Again, it's not completely right, but, you know, we're going to ignore the, you know, the fact that the strange is also part of a doublet. And, you know, once you have this, then of course you can just go ahead and instead of this Lagrangian, just write a Lagrangian with a covariant derivative including the standard model gauge bosons. Yes, so you will have d mu of u. Yes. So this is a 3x3 matrix, yes. One index is an SU3 left, the other is an SU3 right, yes. So you will have something like d mu uij minus igw mu a, and then I will call this matrix now the tau a ik matrix. Yes, so it's now a 3x3 matrix where, you know, you have just an explicit embedding here. Yes, so I will write this as 1/2 tau A ik u kj. Yes, it acts on the left-handed index, and then, of course, I have to embed hypercharge also. Yes, plus I g prime b mu times 1/2 tau 3 right kj, and now this is acting on the second index. Yes, it's acting on the SU3 right. Yes, and of course the U matrix is a QQ bar. It doesn't have baryon number, so there's no additional term here. Okay, so this is how you are embedding the interaction with the standard model gauge bosons. And the most important thing about this, and then of course you write again the Lagrangian as f²/4 trace of d mu u dagger d mu u. Yes, so the same thing as you have over here. And the first thing that you notice is that this Lagrangian actually gives a mass to the w and the z. Okay. Is this a shock or not? Well, it shouldn't be, yes, because what we said is that we have embedded SU2 left into the global symmetries of QCD, and we have not embedded it into the vector-like part of the global symmetry of QCD, yes, because the vector-like part would be if, you know, the left and the right-handed transformations are equal, but that's not what we did, yes. We embedded SU2 left into SU3 left. Yes, so it's not living in a purely vector-like part of SU3. So the QCD vacuum actually does break SU2. Yes, the QCD vacuum breaks the electroweak symmetry. Okay, so that's a fact. Okay, so it's not, you know, this is something that is, of course, experimentally true, yes. It does break the Electroweak symmetry, so just QCD itself, without a Higgs boson, would already give you massive W and Z. Okay, so the W and the Z get part of their masses from QCD. From the QCD vacuum. Okay, so you can just go ahead and calculate how large a mass are you going to get here. Yes, well, what you're going to do here is, yes, you will just put in the unit matrix, yes, because that's the piece that is going to give rise to mass terms for the W and the Z. You just put in the unit matrix, the unit part without the pions, yes, into your chiral Lagrangian, yes, and that's what the mass term is going to come from. Yes, so you can go ahead and explicitly calculate that, and what you will find is that the mass of the W will be G squared F squared over 4 W mu plus W mu minus, and the mass of the Z is going to be G squared plus G prime squared over 4 F squared times 1/2 Z mu. Okay, so it's literally the same expression as the mass term that you're getting from the Higgs in the standard model. The only difference is that V is going to be replaced by the scale F. Okay, so but otherwise, for example, the ratio of the W and the Z masses is coming out exactly right. Okay, and we'll come back to that at some point, because this is also not, I mean, it looks like a surprise, looks like a miracle, but it turns out it has a deeper reason, which is called custodial symmetry. Okay, why this expression, even though there's no scalar field here at all, yes, it's just purely the dynamics of QCD, yes, produced the mass of the W that looks exactly like the mass of the W and the Z in the standard model with the Higgs boson with an elementary scalar. Turns out that there's a symmetry reason for that, and we'll get back to that probably tomorrow or on Thursday when I briefly mention custodial symmetry. Okay, so it has the same structure as in the standard model from the Higgs. Yes. But of course, again, remember, this is not coming from the Higgs. This is coming just from QCD. Okay. And then the question is, of course, you know, so how large is this? Well, it's as large as F is. Yes. So how large is F? Well, how do I fix F? Well, so that you can actually fix now that you have the interaction with the W's by looking at the decays of the pions. Yes, so what you will find is that this term here, yes, will actually also contain an interaction term between the W and the pion. So there will be a term that is G over 2 times F W mu plus D mu pi minus plus Hermitian conjugate. Yes, so this F is going to give you sort of a mixing between the W and the pion. Yes, again, it's not a shock. Yes, because QCD breaks the Electroweak symmetry. Yes, if there was no Higgs, something would have had to provide the longitudinal components of the W and the Z. And in that case, it would have been the actual physical pions, the ones we are observing. Now, what happens in reality is that there's also a Higgs. Yes, it has a much larger VAV. So the Eaton Goldstone bosons are to a very large fraction the Goldstone bosons coming from the Higgs, and a very small fraction of that is going to be in the physical pion. Yes, and the physical pion again will contain a tiny little piece from the Higgs. Okay, so to leading order we'll just say that this is actually the physical pion. Yes, and then we can go ahead and calculate, you know, what, you know, the the decay of the pion will look like, yes? So we can take this mixing here with a W, and then, of course, the W just goes to a muon and the neutrino, yes? So you can go ahead and take this as a derivative mixing proportional to F, and so that's why this F is called the pion decay constant, yes? Because that's the one that is going to give rise to the decay of the pion, and you'll find that F pi is 130 MeV. Okay, again, you just fit this to, you know, the experimentally observed lifetime of the pion, and you find 130 MeV. Okay, so the answer is yes, QCD does give rise to a mass of the W and the Z, but it's less than a GeV. Okay, so it's very small. So in reality, yes, QCD does contribute to the mass of the W and the Z, but you know, in the mass itself is less than 1%. In the mass squared is a tiny, tiny fraction. Yes, but it's there. Okay, very good. So that's conceptually important. Now, the other really important conceptual question is how to take the explicit breaking into account. Yes. So I was telling you the story that, you know, the pion is massless because the SU3 left because SU3 right is broken in the QCD vacuum. But of course, the pion is not exactly massless. We know what its mass is. And the reason, again, we are not surprised because we know that the symmetries that we were considering are not exact but approximate symmetries. Yes? So then the question is, how do I then translate the symmetry breaking terms into a term that you can write down for the Lagrangian of the Goldstone boson? Okay, so that story is sort of a very important conceptual story, so it's really good to try to understand how to do this. So it is called Sporran Analysis, and it's sort of a trick. Okay, so let's do explicit breakings. Okay, so how to do this? So let's start, for example, with the quark masses, yes? So what we said is that, well, there's a term, Q bar MQQ, that is present in the Lagrangian, yes? And the way we started out is saying, okay, let me take this term to 0, and then in that limit, of course, there's an SU3 left plus SU3 right global symmetry. Now we are trying to ask the question, but this term is not 0. Yes, what is its effect on the Goldstone masses? Okay, so how to include this? Of this on U. Yes. Well, so that's where this trick about spurions is coming in, and it's, I think, a good idea and a good place to try to explain what exactly Sporran analysis means. What it means is that, well, what I have over here is a term that is actually not symmetric. Yes, it's a term that is truly not symmetric under the SU3 left cross SU3 right global symmetries. Yes, and the reason why it is not symmetric is because I have this explicit mass term. So the idea of the Sporran analysis is to say, okay, so what would it take to make this term actually symmetric under the full global symmetries? Okay, so well, if this M was not just a set of numbers, yes, but if it was an actual true field that transformed also under the SU3 left cross SU3 right symmetries, yes, then of course I could make this term also symmetric. Yes, so if M, let me say MQ was actually a field, yes, that itself transformed under SU3 left cross SU3 right. And how should it transform? Well, just the opposite way as Q bar Q. So it should also be a bifundamental under SU3 left cross SU3 right. But if this was a 3-3 bar, then MQ should be a 3 bar 3. Yes. So if this was actually a field, then this term was symmetric. Of course, I know it's not a field. Yes, I know it's just a bunch of numbers. It's just M up, which is a diagonal matrix of the up quark, the down quark, and the strange quark mass. But for now, let me pretend that it's a field. Yes, and then what's the rest of the story? Well, the rest of the story is to say, well, let me pretend that it's a field, but it got a vacuum expectation value. Yes, so now I'm getting closer, yes, because now the vacuum expectation value I'm going to identify with those numerical values, yes, that I'm seeing in this Lagrangian. Okay, and then I can also imagine that it's actually a very heavy field. Yes, that the field itself, the excitations of that field are not going to show up in my low energy effective Lagrangian because they are integrated out. So the only thing that will remain in my low energy effective Lagrangian is actually the VAV of that field. Yes. So this is really the logic of the Sporran analysis, is to say, let me promote it to a field, imagine that the field has a VAV, but it's also very heavy. Yes. And then I can pretend that what I have here is sort of the VAV of a field that did transform at some point in its life under the SU3 left cross SU3 right global symmetry. Yes. And now what I will do is I will sort of go through the same steps in the effective Lagrangian, in the Lagrangian where I have the U. Yes. And now I'm saying, now let me try to write down an effective Lagrangian, yes, that involves not just the U field, but also this field MQ. Yes, let me add additional terms to my Lagrangian that involves U and the other field. Yes, so for now I pretend that it's a field. Yes, so how would I write a term that involves U and MQ in my Lagrangian? Yes. Yes. Right. Yes. Yes. No. But there was a field. Yes. It had fluctuations. Yes. And what I'm saying is that those fluctuations became very heavy. Yes. So the radial modes. Yes. Again, if there was, I made it somehow heavy. Yes. So, and how did I make it heavy? Again, it doesn't matter. Yes. As long as I say that, well, they're just not part of my effective theory. Yes. It doesn't matter. What I'm saying is that somehow I arranged, so it's sort of a little bit like I don't know if you know about Tuft anomaly matching. Yes. It's sort of a similar kind of argument that says that there was a procedure, yes, where this was actually a symmetric theory, yes, and all the other stuff I removed somehow, yes. So that's what I'm trying to do now, and go through this whole procedure in the effective theory also, without the quarks but with the Goldstone fields, and say, okay, so now I have two fields, I have U and MQ. Yes, this is a bifundamental and that's a bifundamental. Yes. How can I now write down invariance? Yes, well, I can take, MQ times U. Yes, the trace of that. Yes, plus Hermitian conjugate. Now that's another invariant that I can write. Yes. And of course, I have to write some proportionality constant. I'm going to write here some. If this has an F in it, then I'm going to write a mu squared. Okay, it doesn't matter, yes. And now I say, okay, so this was a field, but then now let me go through the same thing, freeze it to its valve, get rid of its excitations, yes, then effectively in the effective theory, this will just look like, the same numbers that showed up in my, more fundamental theory are showing up as spurions. Yes, this is where this name spurion is coming from, as spurions in my effective Lagrangian. And now I have another term, yes, and this is supposed to capture how a particular effective, a particular explicit breaking term can show up in my effective Lagrangian. Yes, so what this procedure is saying is that yes, the symmetry is explicitly broken. The Goldstones will not be massless, but they are not broken in an arbitrary way. I know how it is broken. I know the term that is doing the breaking. Because I know what term is doing the breaking, I can translate what the possible effect of that breaking term can be in my Lagrangian for the Goldstone bosons. Okay. So again, this name spurion is coming from spurious symmetries. Yes. So I take this symmetry that is explicitly broken and make it sort of a spurious symmetry. Yes, and that's why these parameters are now called the spurions. Okay. So this is what is called the Sporran Analysis. And again, it's very simple now. So now this is it. There's an additional term here for my Lagrangian, yes? And I can just go ahead and calculate the effect of the quark masses here, yes? So it will give you a term of the form trace of, this m up, m down, m strange times the pion matrix e to the 2I pi a t a over f. Yes. So you can now go ahead and plus Hermitian conjugate. Yes. So now you can go ahead and calculate, what will be the effect of these quark masses on the pion masses. Yes. And the answer is yes, it will give you a pion mass. How large is it going to be? Well, obviously it's going to be proportional to the quark masses. There will be another proportionality constant. I have no idea what that is, yes. And, well, there will be a 1 over f squared, yes. So the expectation is that the pion mass squared, yes, will be proportional to a linear power in the quark mass divided by f squared, and then I guess there's some, I don't know, is it cubed? Cubed. Still doesn't work. No, it should be just 1 power, yes, times mu squared. Yes, because in the u there was an explicit factor of f, yes, that's why there's a mu squared. Anyway, the important thing is the mass squared for the pion is linearly proportional to the quark masses, and you can do even more, yes. For example, you can take the limit when m up is approximately equal to m down, and then you can just go ahead and expand this pion matrix, yes, and what you're going to find is the famous Gell-Mann-Okubo mass formula. So that's actually a good exercise if anybody wants to do that. So exercise, literally right here, the pion matrix, pi 0, minus pi 0, pi plus, pi minus, etc. Yes. Take the trace and show that m eta squared plus m pi squared is equal to 4 mk squared. Okay, so this is the Gell-Mann-Okubo mass formula. Okay, so that's how you do Sporran analysis. It turns out in QCD there's another source for pion masses, and that's the fact that electromagnetism also gives an explicit breaking of the global symmetries. So there's a second effect. This is the electromagnetic mass splitting. Turns out that gauging QED, U1 E and M, which is subgroup of SU3 vector is an explicit breaking on its own, and there you can actually treat the quark charges 2/3 minus 1/3 minus 1/3 as the Sporran. That could be another good exercise if anybody is interested, and find that the leading term in that case is going to be proportional to trace Q dagger U Q U dagger Q U. Okay. Okay. So it will also give you a mass splitting among between the charged and the uncharged pions. So that's the story of Sporran analysis, and that's again, an important conceptual ingredient that is used both, in this field, and it's used all over the field in physics. Yes, wherever you have symmetries and wherever you have explicit breakings, this is most of the time the way you are trying to deal with that. All right. One more important conceptual issue before we go ahead and actually start trying to build these models explicitly is the issue of the cutoff. So I mentioned that, of course, the Lagrangian that we are writing down is an effective theory. It has a built-in cutoff scale, yes, because I eliminated the radial degrees of freedom, the heavy degrees of freedom from the theory, yes. So it has a built-in cutoff. And the question is, what is that cutoff? How high can it possibly be? Yes, so the question is, it has a cutoff. The physics of the cutoff is that there are new particles that have been integrated out. Yes, those are, for the case of scalar fields, just the radial degrees of freedom. For the case of strong dynamics, like in QCD, well, all the other non-Goldstone resonances, yes, they will show up like in ordinary QCD. Yes, you have light fields, and then you have a characteristic scale for all the other hadronic resonances. Yes, and they roughly show up at lambda QCD. Yes, so we want to see how is that lambda QCD, what is that characteristic scale here related to this pion decay constant that we have used as our scale until now in the theory. So where do new particles show up? Okay. So what is that built-in cutoff lambda? Well, one way to calculate this is to say that, well, at the scale where the new particles have to show up is the scale roughly where the predictability of my theory is breaking down. Yes. So what I'm going to try to do is try to calculate at what scale do the loop corrections calculated within this theory are actually going to be roughly equal to the effect of the three-level terms that are present already just from expanding my chiral Lagrangian. Okay, so the estimate for the cutoff and again, this method is called the naive dimensional analysis. Is to say that lambda is the scale at which perturbation theory within my effective theory ceases to be meaningful. And the way I translate that is to just do a loop calculation in my effective theory, cut off all the divergences at the scale lambda, yes, and say that, well, I will demand that my loop corrections are not bigger than my tree-level corrections. Yes, that's the procedure, again, which is called naive dimensional analysis, which is roughly trying to estimate, what the intrinsic cutoff scale of this theory is actually going to be. Yes, so let's do the example that we have already learned and know roughly how to do it. Yes, what I said is that from my chiral Lagrangian for the pions, yes, I have here f squared over 4. Yes, from my chiral Lagrangian of the pion, I can read off a 4-point interaction for the pions. Yes, and we sort of, did this, though not, in great detail. Yes, what I told you is that the kind of term that I'm going to get is derivatives times 2 pions, yes, times 1 over f squared. Yes, that's roughly how this vertex is going to look like, how this interaction vertex is going to look like. Yes. Now, what I'm interested in is take 2 of these interaction vertices, put it together in a loop, and try to start calculating corrections to my tree-level term that is already present. Yes. So I'm going to take this vertex, yes, take 2 of these, close them up, yes, and try to estimate how large the correction to my tree-level term that is already there is going to be due to doing a loop in this effective theory. Yes. So how should I do that? Well, I think it should. But I don't know if numerically, I think, it should roughly be the same, right? That's another method, yes. You just look at the scatterings and you just ask the question, when does this theory lose unitarity? And I think it should be. I'm sorry? Right. So should be, I think it should be the same. Okay, so let me try to do a loop here. And, okay, so how large is that loop going to be? Well, again, it has 2 vertices, so it will have a 1 over f to the 4th term. Yes. It will have a 1 loop showing up there, so I'm going to write here 1 over 16 pi squared. Yes, so that, well, okay, let me first write the loop and then estimate it. Yes, so there's an integral d for k, yes, over whatever 2 pi whatever to the 4 whatever it is. Yes. How many propagators will I get here? Yes, well, there are 2 pions running in the loop, so there's a 1 over k squared. Yes. But both of these terms were derivative interactions. Yes. So I would have to put in 4 powers of momenta still. Except I know that eventually I'm supposed to get a derivative interaction here. Yes. So out of the 4 powers, eventually, if you did everything correctly, 2 of them have to be converted into external momenta. Yes. And 2 of them can be still loop momenta. Okay. So there should be a p squared times k squared here. Yes. Again, you have derivative interactions at both vertices, so you have to put in 4 powers of momenta, but you know that there will be no contribution. If you did the calculation correctly, you better not get a contribution without any derivatives on on the pions, yes, because this was a theory of the Goldstone Bosons. So there you eventually are not you are not supposed to get a term that is a non-derivative interaction. So you are going to put here 2 powers of external moment that of the momenta will be converted into external momenta, and the rest you are just going to calculate the degree of divergence of this diagram. Yes. And so now what we see is that I will get here p squared over f to the 4. Yes. And then there will be a loop. A loop is generically, eventually, once you go through all the Wick rotations and all the Feynman parametrizations, eventually usually gives rise to a one loop factor that is 1 over 16 pi squared. Yes. And the remaining integral here is d4k over k to the 4 times k squared is quadratically divergent, so there will be a lambda squared. Okay, so this is what is called the Nda estimate, yes, for this particular loop. Yes. And then what you're supposed to do is you're supposed to compare the magnitude of this operator, yes, compared to the one that is already present at the tree level, yes, from your chiral Lagrangian. Yes, well, that was just, this term, so in terms of a Feynman rule, this would be p squared over f squared. Yes, so this should be p squared over f squared. That should be the magnitude of it. Yes. So what you see is that, well, if you want to make these two roughly equal at most, yes, that will give you an upper bound on what the cutoff should be. Yes. What you find is that lambda squared over 16 pi squared f squared is equal to 1. Yes. So what you find is that lambda is equal to 4 pi f. Okay. So this is what would be the Nda estimate for the intrinsic cutoff scale of this theory. And again, what this tells you is that at the latest, yes, at this scale, some new particles have to show up. Of course, there's nothing that will prevent you from possibly having the new particles showing up earlier. Yes. But at the latest, there's gotta be some new particles showing up at that scale. Okay. Right. It's sorry. Well, I mean, if you're asking, is there possibly a factor of 1.5? Yes, I can imagine that. But could there be a factor of 10? We have not seen any example of theories like that. Okay, so this works always. Always true that yes. If loop correction is much bigger than 3 level? Well, again, the way we are interpreting that is that that's the sign that your that your theory as an effective theory has broken down. Yes, that's the sign that some new particles have to have appeared already. But okay, maybe next terms they will like flat. Again, that's why it is Nda. Yes, it's the naive estimate, and again, it works really well, and. If you're asking, tiny deviations from it, like 50%, yes, possible. Factor of 10, I don't think we have ever seen. So, but what I'm saying is there could be particles earlier, yes, but you can't go the other way. Earlier is possible, absolutely. That's what I want to get to. And so earlier is possible. So this is an upper bound on the scale where new particle masses show up. Okay, there could be new particles showing up earlier. Yes, for example, if you try to apply this to the Higgs effective theory, yes, of course the Higgs shows up, much earlier than, the mass of the actual Higgs is, is root 2 lambda times V, yes, is not 4 pi times V, yes, I mean, whatever lambda is, yes. So basically what we say is that if there is a weakly interacting particle, it's like the Higgs, then it can show up earlier. Okay? If all the particles are strongly interacting among each other, yes, you expect them to roughly show up at that scale lambda. So weakly interacting particles or bound states can show up earlier. So for example, like I said, for the case of the Higgs, the characteristic self-interaction scale is self-interaction strength is given by its quartic coupling. Actually, usually it's the square root of the quartic coupling. Yes. So for example, MH is root lambda times V. Yes, there's a factor of 2 there also. Yes, and this one is roughly, the scale of the characteristic self-interaction strength of the Higgs. Yes, so the expectation is that if there is a weakly interacting particle whose characteristic interaction strength is G star, then it is going to show up at the scale G star F. Yes? If all the bound states, if all the bound states are strongly interacting, so G star is 4 pi, yes, then you're going to get the, that scale that I have over there. But there are some particles that could show up earlier. Yes? Right. So it's almost, so it's almost 4 pi. It's a slightly more weakly interacting than, the maximum interaction strength.
So by earlier you mean like at 10% of it?
Could be at 10% of, for example, the Higgs, yes, is not showing up at 4 pi V, yes, but lambda is 1/8, yes, so it's the square root of that, so it can be earlier, yes. If some of these particles are weakly interacting, they're going to show up roughly at the scale that is given by the characteristic interaction strength of them. So the rho is actually, not quite, fully strongly interacting, yes, so it shows up a little earlier than that. Okay, so that will be actually really important for us, because what we will have eventually in most of these little Higgs and composite Higgs theories, we will have some of these particles that are showing up before the cutoff scale of the theory. Yes, and those particles will actually eventually be identified with what we will call the top partner and the spin 1 partner of the standard model gauge bosons, and it's important that they show up before the cutoff scale. If they show up at the cutoff scale, then it's too late. They can no longer help you with cutting off the quadratic divergences. Well, so the theory on its own would be consistent up to those scales, could be consistent up to those scales. There can be other particles possibly showing up earlier, yes, but that theory just on its own would definitely break down at this scale. Will definitely break down at this scale. Well, it works until this scale without any additional particles, yes, but it doesn't mean that there are no additional particles showing up. Yes? I'm sorry? Well, the question is what it means working, yes? Meaning, is it consistent or is it the right theory of nature, yes? It's a consistent theory, yes? It happens that there are some bound states that are lighter, yes? So you better include them if you want to describe experiments, you know, at the scale where the rho is already there. But, you know, the theory would have been fine without the rho. It's just not the right theory of nature. Yeah? So this is just saying the theory is truly becoming sick, yes, at that scale. So you really shouldn't even imagine working with this theory above that scale, yes? But what I want to emphasize is it doesn't mean, of course, you know, that you know, it solved all the dynamics of QCD, yes? I mean, but it doesn't mean that, you know, there cannot be anything happening earlier. Yes, that's exactly what I'm trying to emphasize. There can be LiDAR states. Yes, it's, you know, there, you know, most, you know, the expectation is that most of the generic bound states are going to be living at this scale. Yes, there could be some that are for some reason LiDAR. Yes, that's the generic expectation. Okay. And again, this is going to be important because, you know, we will assume in most of these theories that there are some particles that are special. Yes, those will be, again, you know, the ones that are going to actually cancel the quadratic divergences of the top and the standard model gauge bosons. And if they show up at the cutoff scale, that's too late. Okay, so we will have to make the assumption that there are these relatively light new particles. All right, so I will skip the part about the generic Nda estimates for the magnitudes of the Lagrangian. So maybe, Javi, that's a good topic of discussion if there are no other questions. What I would like to say is now, so we are basically done with, you know, just discussing the generic properties of Goldstone bosons. Now I would like to, you know, end this lecture by sort of, you know, previewing for how we are going to actually use this for building, you know, these composite Higgs models. Okay, so how to use this for composite Higgs models or related ideas. Well, of course, as I mentioned in the previous lecture, the simplest idea would have been to say that, well, QCD breaks the electroweak symmetry. It gives a mass to the W and the Z, as we saw. It just happens to give it a mass that is too small. Yes. So the simplest idea would have been to just scale up QCD meaning, you know, take another QCD-like theory where lambda QCD is not of the order of 1 GeV, but it's something of the order of 1 TeV. Yes, so 3 orders of magnitude bigger. Yes, so lambda QCD is of the order of a TeV. Yes, so that would have been called Technicolor. Yes, such that, you know, this scaled up version of QCD has, you know, so this Technicolor would have an SU2 left cross SU2 right global symmetry, just like QCD, and the quark condensate breaks that global symmetry to the diagonal one. We embed the electroweak interactions, just like for QCD, into the SU2 left cross SU2 right, and you have electroweak symmetry breaking. Yes, so again, you would have these Techni condensates, Q bar Tc Q Tc proportional to lambda Tc cubed. Yes, and that would break the electroweak symmetry, and that's it. Yes, that would have been the simplest and most elegant solution. Yes, and again, you know, for 2 decades, this was in fact one of the leading theories that people have been examining. Of course, you know, the nice thing about this theory is that it's very different from the standard model. In particular, it predicts the presence of no Higgs-like excitations. So again, you know, this is not the right direction. Yes. So even though it was a good idea, but it's just not what nature has chosen to do. Now, okay, so the next direction would be to say, okay, so we still want to use some strong dynamics to break the electroweak symmetry, but not in the direct way like with Technicolor, but rather we make the Higgs a composite. Okay, so just proclaiming that the Higgs is a composite itself solves the big part of the hierarchy problem, yes, because the implication of that sentence is that actually there are no fundamental scalars, that, for example, these are composites of a theory made out of just fermions. Okay, so that's fine, except in a generic theory, yes, what you would expect is that there is a scale of compositeness lambda, yes, and most of the composites are living at that scale, so the Higgs would be living at that scale too. Okay, so, well, that's not so good, yes, because, well, either I take the scale of compositeness to be 100 GeV, yes, and then, well, I would have had to see, you know, hundreds of new bound states already probably at lab. So either lambda is 100 GeV, so that's no good, yes, because it's already excluded by lab, by Tevatron, by, you know, many, or lambda is 1 TeV, yes, but that's also not good, yes, because the Higgs is not 1 TeV, yes. So then the idea is to say, okay, very good, so the Higgs is not one of the generic composites, yes, it has to be lighter, much lighter than the scale of compositeness, so I will make the Higgs a Goldstone boson. Okay, so now the Higgs is 125 GeV, but leaving the scale of compositeness at 1 TeV is still very problematic. Okay, because again, the expectation would be that at this scale, 1 TeV, there would be a very large set of bound states showing up, and they would give rise to, even without, let's say, you know, if you say that, okay, it's not 1 TeV, but 2.5, such that the LHC hasn't seen it, but it would give rise to all kinds of higher dimensional operators just for the standard model particles. Yes, and that would give rise to very, you know, a lot of electroweak precision corrections. Okay, so a generic theory with lambda equals 1 TeV is problematic because of electroweak precision tests. Okay, so the usual approach is to take lambda one more order of magnitude bigger. Yes, so to take lambda is 10 TeV. Okay, so then we are safe from generic electroweak precision corrections. However, now there is another problem, yes, because making the cutoff scale 1 TeV and keeping the Higgs at 125 GeV, that's kind of a natural ratio, yes, because if I now calculate a quadratically divergent loop correction with 1 TeV and I put a loop factor 1 over 16 pi squared, that's something of the order of 100 GeV. Okay, so this ratio is roughly okay, yes, but once I push it to 10 TeV, yes, keeping the Higgs at 125 GeV, yes, even if it's a Goldstone and a generic theory is not going to work, because as you will see, making the Higgs a pseudo Goldstone boson rather than a true Goldstone will generically reintroduce quadratic divergences proportional to the scale lambda. Okay. So you will get corrections of the order lambda squared over 16 pi squared. Yes. And now you will want to push the Higgs mass up from 125 GeV to 1 TeV. Okay, so this is what is called usually the little hierarchy problem. Yes, that in a theory with a cutoff of 10 TeV, the Higgs is actually not natural at 100 GeV. It would be more natural, it would be natural at 1 TeV, but there is a percentage kind of tuning, yes, when you are going from 1 TeV down to 100 GeV. Okay, so all the model building that we are going to be doing that goes into composite Higgs and little Higgs type models is actually to avoid this one loop quadratic divergence here. Okay, so that's what we'll be continuing in with tomorrow. So there's a really nice way to make sure that actually in a theory like this with a 10 TeV cutoff, yes, the one loop quadratic divergence is going to be cancelled, yes, for the Goldstone boson, and that's what is called collective symmetry breaking. Okay, so that's going to be the topic for tomorrow. Yes? Right. So how far are we? Well, so that's a good question, yes. So if the Higgs is composite, then it will have deviations from, the interactions of an elementary Higgs, yes. So we will quantify that later on and see, how far we are, how to quantify it, what is the relevant quantity there, and so that's something that is going to come up. Yes. Right. So the whole next lecture will be about how to make it a pseudo and still not get a one loop quadratic divergence. So that's called collective symmetry breaking. Any form of explicit breaking generically reintroduces the quadratic divergence, and there is a nice idea called collective breaking that is telling you can have sort of, play some tricks where you make it a pseudo, yet the quadratic divergence is not going to show up at one loop. And here, what I should also emphasize is that now you're only canceling the quadratic divergences at one loop, and the two loop is already okay, yes? Because you're only worrying about something, proportional to 10 TeV, yes? So when you take a two loop quadratic divergence from 10 TeV, yes, that's already small enough. That's roughly already an order 1 correction to the mass of the Higgs. Yeah? So it's different than supersymmetry where you're really canceling to every order. Yes. So this collective breaking itself doesn't solve the hierarchy problem, but combined with the idea of compositeness, it can. That's sort of the story here.